Tidal energy is a form of hydropower that converts the energy of the tides into electricity. An emerging technology, tidal power has significant potential for future electricity generation and to become an integral part of the energy mix. Energy derived from the tides is more predictable than wind energy and solar power. It can be scheduled into the grid with certainty. There are three main ways in which power can be generated: tidal barrages, offshore tidal lagoons, or tidal stream farms. In this programme, we're going to take a look at tidal stream energy.
And joining us to tell us more is Mike Smith from marine power company Atlantis. Many thanks for joining us, Mike.
It's a pleasure.
Explain for us the principles of tidal stream energy. I guess it's coming ultimately from the rotational energy of the spinning Earth.
Yes, it's the moon pulls the ocean closest towards it and creates a bulge in the Earth's surface, and the spin of the Earth creates a bulge on the other side of the planet as well. And as those two bulges move around as the Earth spins, the water tries to move around the land masses, and where the water gets, where the land masses constrict it, the water flow velocity increases, and that's what we're trying to capture.
So, and how do we actually? What's the infrastructure necessary to capture this energy?
It's basically it looks like a wind turbine, but on a much smaller and much beefier scale. The water is much more dense than air, and therefore we can put a smaller unit in under the water that you don't see, and the spinning blades convert the kinetic energy of the water through a generator into electricity.
Now, give us some figures here. A comparison, say, with wind energy. So, say a speed of 2 knots, 2 meters per second. What equivalent wind power would be necessary? What equivalent wind strength would be necessary to derive the same sort of power?
If you take 2.5 meters a second, which is about 5 knots, the equivalent wind speed would be around 350 kilometers an hour.
Wow.
To put that in perspective, 120 kilometers an hour is hurricane force. So it's 3 times hurricane force. And we get the same amount of power out of that water at 2.5 meters a second as you would out of wind flowing at 350 kilometers.
So you get more bangs for your buck.
You get far more bangs for your buck.
Excuse the non-technical term. Okay, what about other schemes? Are there any schemes in the world? How widely has this been taken up?
There's 3 types of sort of tidal energy. There's tidal barrages and lagoons, which tend to be linked together, and then there's tidal stream energy. For tidal stream energy, we've had a unit on test in Australia since 2006. The EMEC Centre here in the UK, which is European Marine Energy Centre up in the Orkneys, is a test centre for renewable devices, and that's Open Hydro deployed a device there 2 years ago. That's on test. And Rolls-Royce are, with TGL, are deploying it as we speak at the moment. And we'll be putting our 1 megawatt unit in at EMEC later on this year. So there'll be 3 up there. The first grid-connected unit in the UK was at Strandford Lock. Marine Current Turbines installed that in 2008. But in total, there's less than 2 megawatts of energy at the moment in the UK.
But it's an emerging technology.
It's very much an emerging technology. By the end of this year, there'll be 3 to 4 megawatts, and as we go on, that will increase dramatically.
Okay, let's run through the other types of tidal energy. Barrages, how do they work?
Barrages simply are used to, they dam up an area like the Severn Estuary, and as the incoming tide rises, the dam is then closed, or the barrage is closed, and then on the ebb tide, when it flows out, it stops the water flowing out through the barrage until they want to release it, and then it spins a standard Pelton type turbine and generates electricity.
Drawbacks?
Drawbacks really are that upstream of that it creates quite an environmental issue, and that's one of the things that is challenging for the Severn development at the moment, and other areas that it's being looked at.
Okay, let's move on to offshore tidal lagoons. Tell us a bit about those.
They're very similar, but instead of just damming up one edge of it, you effectively have to create the whole barrage.
So that's quite a bit of infrastructure
It's
necessary.
a lot more infrastructure, so it's more costly, but it doesn't have quite the same environmental impact. It still does have environmental concerns, but yes, it's a much more costly way of doing it.
And other places in the UK that...
There are 3 places in the UK, the Wash, the Severn, and off Blackpool, basically.
So what do you think the potential is for tidal energy in general and tidal stream energy in particular?
In the UK, the potential is well in excess of 10 megawatts for tidal energy. If the Severn development goes ahead, it's a couple of gigawatts. The Pentland Firth, which is where the main tidal resource is, could well be in excess of 10 gigawatts. There's lots of people say it's 2 to 3. There's lots say it's more than that. But overall, I would say there is at least 10 gigawatts of tidal energy extractable in the UK.
So what proportion of the UK's energy demands, what proportion could tidal stream energy and tidal energy in general contribute? What sort of percentage are we talking about?
A significant amount. The tidal energy is predictable, which is one of its main advantages. But we're talking in excess of 10 gigawatts of energy, and that's enough to power 2 million homes.
So it's a considerable proportion.
Considerable proportion, yeah. You could get 5%, which doesn't sound a lot, but that is a considerable proportion.
It certainly is. Okay, that's a bit of background. Let's take a look now at some rough estimates of tidal power.
Follow a high tide as it rolls into the UK from the Atlantic. The time of the high tide becomes progressively later as we move east up the English Channel from the Isles of Scilly to Portsmouth and on to Dover. The crest of the tidal wave progresses at about 70 kilometres an hour. Similarly, a high tide moves clockwise around Scotland, rolling down the North Sea from Wick to Berwick and on to Hull at a speed of about 100 kilometres an hour. These 2 high tides converge on the Thames estuary. The power that we can extract from the tides can never be more than the total power of these tidal waves from the Atlantic. This power has been measured to be about 250 gigawatts in total, which shared between 60 million people is roughly 100 kilowatt hours per day per person.
Now these are only rough estimates. Presumably flow modelling is crucial for any scheme.
Yeah, I mean, flow modelling is fundamental for tidal energy, and we have to get it right. Yes, we're going through testing at places like EMEC, but flow modelling is the basis for developing the financial model, which is where we get our investors to come on board. Flow modelling is an art that's been developed, the software to analyse it by DHI through their Mike software.
DHI, what does that stand for?
Danish Hydraulic Institute. Right. And Mike, no relation of me, is the software. That's what they've called the software. It's just Mike software.
Okay, just tell us what you get out of relative flows. Does subsea topology contribute? Say you've got a flow of 3 metres per second in America, say, and in Scotland, do you get the same amount of energy out of both?
It's very dependent on the topography. As those bulges move around the Earth and they get constricted, it's very, very dependent on the topography they go through. So, for example, as Atlantis, we looked at a site off Long Island and a site off Scotland. They both saw approximately the same flow speed at 3.1 metres a second, but because of the duration of the flow going through that constriction in Scotland, we would get, once we put that through our power curve, we would get 3 times as much power out of the Scotland resource than the Long Island resource. And when you look at them at face value, they both look to be exactly the same.
So in engineers' parlance, friction losses,
yeah.
You have to take into account friction losses in any scheme.
Absolutely.
Okay, tell us how you would undertake a process of tidal flow modelling. What would you go through?
We go through a series of deployment of, when we look for a resource, we go out with boat-mounted ADCPs, acoustic Doppler current profilers, and we go out and try and find the resource in the first place. And then when we've found a resource that is that we think the flows are good at, we'll deploy a fixed bottom mounted ADCP and analyse the data in detail. Then once we've collected all that data, we then
How long do you have to collate data over?
That collation period could be over a period of a year. So it's not a short-term thing. And then we have to look at the tidal range in that area to work out where the water surface is as it goes through the 24-hour cycle. We look at the topography, so we have to do bathymetric survey, very detailed bathymetric surveys. Then that's all input into the model, this DHI mic software. And then once we analyse that, we then put our individual turbines into that model. So we might have 100 turbine locations that we want to place on the seabed. And we optimise the output because each of those turbine locations is a sink. It's extracting energy out of the water flow. So as we move those about and as we space the distance between the turbines, it alters the ultimate output that we get.
So very detailed modelling.
Very, very detailed modelling, very sophisticated, massive amounts of computer power.
And I suppose the financial viability of any scheme depends on scale.
Correct, yes. It depends on scale, but it also depends on the power price. There are some fabulous resources around the world, but they have no power price. So there's nowhere to get the electricity away. They also require a load. So if you get a resource that has absolutely no inhabitants around it or no grid connection, you're not going to get it away. So it's a combination of resource, location, but primarily power price. So how much money do you get paid for your electricity?
And how much of a subsidy do you get from the government?
It's under review. The UK government has a ROC scheme in the
renewable
obligation certificates, right. and in rough terms, if the brown power price, there's a brown power price component, which is how much you get as if you were generating from a coal-fired power station, for example, and then there's ROCs, and each ROC is roughly equivalent to one. If you say the brown power price is £50, a ROC is roughly equivalent to £50.
So there are subsidies.
So there are subsidies. So if you're getting and dependent on the technology, the ROCs for wave, the ROCs for tidal, the ROCs for wind are all different. So if you've got wind, you're getting 1.5 or 2 ROCs. If you've got tidal, you're getting 2 ROCs in the UK, 3 ROCs in Scotland. If you're wave, you're getting 5 ROCs in Scotland.
Okay, let's have a look at the technology in a bit more detail.
Tidal stream generators draw energy from currents in much the same way as wind turbines draw power from the air. The higher density of water, roughly 800 times the density of air, means that a single generator can provide significant power at low tidal flow velocities compared with wind speed. Therefore, water speeds of about 1/10 of the speed of wind provide the same power for the same size of turbine system. Given that tidal currents of 2 to 3 knots or meters per second are common, there are many places around the UK where the power per unit area of tide farms would be 6 watts per square metre or more, twice that of wind farms.
Okay, what sort of target flow velocities do we need?
We typically look for areas with water flows of about 2.5 metres a second or 5 knot flow. And that gives you a maximum flow somewhere around 4 to 4.5 metres a second, 8 to 9 knots. Those are typically the flows we're looking for.
So give us a sense of scale here. Those considerable flows?
They're considerable flows, yes. I mean, there are lots of areas in the world with flows greater than that. For example, the Channel Islands sees flows much bigger than that. The Penton Firth certainly sees those flows.
That's in Scotland? In
Scotland, yes. Anglesey sees them. So there's lots of locations around the UK that see those flows. There's flows in France that see that.
And what about water depth? What sort of depths do you need?
At the moment, we're typically looking for 30 to 50 metres of water because of the nature of our turbine. Other developers are looking for deeper water than that, 60, 70 metres. But as the technology is developed and the turbines get bigger, the water depth will increase. So at the moment, we're going for the near shore locations.
Now, we've all been past wind farms and seen the blades going round or not, as the case may be, depending on if there's any wind resource. What sort of revolutions per minute, say, do you need for tidal stream energy?
Ours are very slow. They're very slow and very high torque. So we typically see, in the range 6 to 15 to 20 revolutions maximum. So they're going around slowly, and the tip speed of the blade is quite slow.
And what sort of percentage of the incident energy can you expect to extract? How efficient are the turbines?
The turbines themselves are efficient. It's really blade efficiency is the key, and if you have just a standard blade profile, you would expect to get an efficiency of 25%. Ours aren't standard blade profiles. We know we have the most efficient blade in the world, and we're able to extract over 40% of the energy out of the water. Now, if you were to put in thousands of turbines, it would be a very high percentage, but you would undoubtedly do a lot of environmental damage to the surrounding areas. So what we typically look for is a slow build out. So we will put a few turbines in, we theoretically model them, and we theoretically model the effects, but we're working with the environmental agencies to build these farms out slowly, to monitor the effect they have, and then to ensure that we do absolutely zero damage to the environment.
I'd like to ask you about costs. What are the factors influencing the costs of energy production?
Very much water speed. We talked about it earlier. The faster the flow of the water, the more energy you generate. But the faster the flow of water, the more robust you have to make what you put down in the seabed. So it's a bit of a double-edged sword. So that's one factor. Topography is another factor, the foundation, the distance from shore, the grid infrastructure that you've got there. They're all factors that weigh on the finances.
Now, cost is everything. Let's have a look at the factors influencing cost in a bit more detail, and some other key issues as well.
The total cost of energy will depend on the flow velocity distribution over each 24-hour period, measured in metres per second, the direction of the flow on the ebb and flood tide, water depth, distance from shore and point of electrical connection, geotechnical properties of the site, and availability of construction vessels to deploy the turbines. Other issues include: how do you connect to the grid? What will the power price be? Is there a process for a seabed lease, and what permits and consents will be required? For example, will an environmental impact assessment be necessary? Where would the cables come ashore? Through sand, for example, or by directional drilling through rock?
Okay, let me pick out a few key issues. How does flow velocity, you sort of touched on this earlier, influence cost?
Flow velocity has a significant influence on cost. As I said earlier, we typically look for 2.5 to 4 metres a second flow. There are areas that see significantly more flow than that, but at the moment we're not looking to put our turbines there because it's a bit of a double-edged sword. You want faster flow to generate higher revenues because it's cubic. So a 2.5 metre per second flow versus a 3 metre per second flow, you get 50% more power out of it on the 3 metre per second flow. So we're looking for fast flowing water, but the faster the flowing water, the more robust we have to make the turbine, and therefore that's more cost. And more cost for the blades, more cost for the infrastructure.
And I assume intermittency is important as well. You want a continuous flow rather than gaps between periods
Absolutely.
of fast flow.
Yeah. We'd much rather find a site that has large continuous flow or a decent value of average continuous flow rather than want a site that has larger flow but it's more intermittent. And that was one of the differences between the Long Island site and the Scotland site.
And what about the direction of the tide?
Very much we would like the tide to come in and out in the same direction, but unfortunately it doesn't always do that. But that's what what you're looking for ultimately. The reason for that is if the flow doesn't come in and out along the same line, you then have to put a rotate unit in to your turbine system, which is added cost, added maintenance, more complexity. And we're looking for turbines where they're as simple as possible.
Now let me ask you about ground conditions, which dictate the cost of any civil engineering project. Are there ideal conditions that you would want? Would you want sand to make laying of the cables easier, or directional drilling through rock, for example?
Well, very interestingly, Martin, most of the areas we look at, because the water is so fast flowing, it tends to have scoured and blasted everything away. So we generally tend to end up with rock seabed. So we can't trench cables. So it's much more difficult for us. But having said that, it makes it easier in terms of the foundation design because we've got solid rock to go onto. So we we tend to use solutions that basically sit on the rock rather than are piled into it like wind turbines offshore, for example.
So what sort of civil engineering techniques would you use to lay the cables and the associated infrastructure?
Within the array itself, we would lay the cables and almost staple them to the ground with a specialist tool so that they don't flap around. But when we're trying to evacuate the cables, we tend to go for directional drilling through the rock. Because we're more near shore than the wind farms, we tend to find that we're very protective of the environment, very protective of the coastline. So even if it costs a bit more to do directional drilling, we will do it rather than dig a beach up.
And as you've just said, and it's worth emphasising, these schemes are built very much close to the shore.
We're very close to the shore. We're within 1 to 2 kilometres of the shore. So if you were able to see the turbines, you would be they'd be quite visible from the shore, but you can't see them because they're underwater. You can actually see nothing. That is one of the fabulous things about tidal energy.
Now this is a very exciting area, potentially 5% of energy demand, as you said earlier. How do you see things developing over the next, say, 5 to 10 years?
It'll be slow to start with. There's so much consenting to go through and in the environmental impact assessments that we have to go through so that we do it correctly. What we don't want to do is just charge ahead and get it wrong. So we're very cognizant of that. So over the next 2 to 3 years, you'll see lots of testing at places like EMEC. You might see 1 or 2 small mini arrays of 6 to 10 megawatts, but the big 100 megawatt projects won't come until the middle of this decade, somewhere around 2015. But by 2020, I would expect to see between 1 to 2 gigawatts of energy available, which is a significant amount.
How many power plants could that displace?
That'll displace at least a couple of nuclear power stations.
So very much part of the global energy mix.
Very much part.
And the domestic energy mix.
And domestic. And the thing is, everybody likes it.
I'm afraid that's all we've got time for, Mike. Thank you very much for your insights. This has been a very interesting topic and one we should watch in close detail.
Absolutely.
Don't forget, there's more in the study notes as usual. However, for now, from all of us in the studio, goodbye.